All right, these are your 5.1 notes, and we are going to be looking at composite functions. Okay, so composite functions, you guys definitely learned these in Algebra 2, and I've seen you make the mistake of this a lot because we've learned function operations so far. The book is kind of funky where it breaks up function operations, and I know that you guys have a general idea of what this is because when we do function multiplication, it is not an uncommon mistake to see somebody give me a composition function. I use a dot for my multiplication symbol. We assume that that multiplication symbol is the open circle, which represents function composition. And you've shown me that you have an idea of what function composition is. So composite function is given two functions, f and g. The composite function denoted by f of g of x, well, that's the way I read it, but it technically is read as f composed with g. I'm always going to read this as f of g of x. So f composed with g of x is equal to f composed with g of x. Or the bigger idea here is that my input x into f of x becomes my function g of x. Like I'm putting in the entire function g of x into f of x to give myself a function. The domain of the as f composed with g of x is the set of all numbers x in the domain of g such that g of x is in the domain of f. And we're going to look at what this example means. I'm going to show that to you. That's a really mathy definition. All right, and then so this is a meme that was shown to me by a former student to kind of help you with a composite function. So I've got f and g of x. If I've got f of g of x, that means I'm inputting g of x into f of x. So if f of x is a pizza and g of x is a pineapple, f of g of x means that I'm putting pineapple on my pizza. If I've got g of f of x, that means I'm putting pizza on my pineapple. I'm inputting that pizza into the pineapple for f of g of f of x. For f of g of x, I'm inputting that pineapple into my pizza. All right, so evaluating a composition function. So f of g of 1, first thing that we can do is we could find g of 1, which means that I have 4 times 1. So g of 1 is equal to 4. Now that I have this, I input that, and I have f of g of 1, which I guess I could have written that at the beginning, that this is the same thing. So now that I have that, I know that g of 1 is equal to 4, so I'm looking at f of 4. So then f of 4 is equal to 2 times 4 squared minus 3, which is 2 times 16 minus 3, which will be 29. So if I am given a number and I want to figure out what is the value of the composite function, I always work right to left. I plug the number into the right function and then I plug it into the left function. So for example, again, I've got g of f of 3, so that means I'm going to find f of 3. So 2 times 3 squared minus 3, 2 times 9 minus 3, this is 15. Now that I know that this is 15, I need to figure out what is g of 15, which is equal to 4 times 15, which is 60. So g of f of 3 is equal to 60. I figured out what f of 3 was. Once I had f of 3, I plugged it into g. I found g of f of 3 to be 60 because f of 3 is 15. G of 15 is 60. We can do this over and over. If I have f of negative 1, that means the first thing I need to do is find, okay, what is f of negative 1? F of negative 1 is equal to 2 times negative 1 squared minus 3. This is 2 times 1 minus 3. This is negative 1. So now that I have that, I will plug that into f, which just happens to be negative 1 again. And I've already found that f of negative 1 is negative 1. I already did that work. So there we go. I can say that f of negative 1 is negative 1. F of negative 1 is negative 1 because I found what f of negative 1 was. Once I figured out what f of negative 1 was, I plugged that y value back in as a new input into that function f and went from there. G of 5 means I need to figure out what g of 5 is. So that's 4 times 5, which is 20. So g of 5 is 20. And then I need to figure out, all right, what is g of 20? And so that's 4 times 20, and that is 80. So that is how I figured it out. I found out what my first one was, which is my rightmost function. I plug it into my rightmost function, and then I plug it into my left function. All right, so now we're going to do it a little bit different. So given f of x is equal to x squared plus 3x minus 1, and g of x is equal to 2x plus 3, find f of g of x and state its domain. So this is saying the exact same thing as f of g of x. G of x is on the inside here. It's also the rightmost function, so that means I'm plugging g of x into f of x. So that means that when I do this, f of g of x means that I've got 2x plus 3 squared plus 3 times 2x plus 3 minus 1. I'm plugging the entire function of g of x into x, and now I'm going to expand it. This is kind of like what we did in chapter 2 when we had these, when we were looking at functions and we were looking at the basics of functions and we were looking at function operations. If I'm given, like my input here is an entire function, so I just go through and evaluate it. This is on your final. You guys did pretty well at this. So this is 4x squared plus 12x plus 9. That's when I square this. Plus 6x plus 9 minus 1. I combine these. So f of g of x is now combining my like terms. I've got 4x squared plus 18x plus 18 minus 1. So this is f of g of x is equal to 4x squared plus 18x plus 17. So that's what f of g of x is. I plugged my entire function of g of x into that x, and then I expanded as needed. Now I can say that my domain here, well, this is where these are really easy because these are both polynomials. So my domain of both of these is all real numbers. You got to love working with polynomials because when both have all real numbers as a domain, your new domain is just all real numbers yet again. Nice and simple. I like it that way. Now I'm going to go back up here and actually show you something different. So let's look at this g of f of 3. What I could have done is g of f of 3 is the same thing as saying g of f of 3. What that means is I could have plugged, the first thing I could have done is found g of f of x by plugging in f of x into g. So I could have said 4 times 2x squared minus 3. So I could have ended up with 8x squared minus 12. Then I could have plugged 3 into this g of f of x function. And I could have said 8 times 3 cubed minus 3 squared, not cubed, sorry. 8 times 3 squared minus 12. That's 8 times 9 minus 12, 72 minus 12. And when you look at that, it's equal to 60. And it would be a problem if they weren't equal. That would show you that the math doesn't work. So I could have done this that way as well. I could have plugged in f of x into g of x, figured out what that composition function is, and then plugged in the number. I tend to do this way more often. That's just how my mind works. I find my actual composition function, and then I plug in my number. So over here, we'll look at this first example, f of g of 1. We already know here that my answer is 29. We have all of that here. And again, I could figure out first, this is the same thing as f of g of x. I could look at what my composition function is. So that would be 2 times 4x squared minus 3. So that's 2 times 16x squared minus 3. This is 32 times x squared minus 3. My x squared here is just 1. So that's 32 times 1 squared minus 3. 32 minus 3, and would you look at that, that's 29. So I figured out here that this was my f of g of x composition function. I knew it. I plugged that 4x into the x of f. I figured out what that function was, and then I could plug my numbers in from there. So that's another way that you can do that. You don't have to do it that first way I showed you where you find g of 1 and then plug that y value into f and then figure out what it is. You could just move straight to finding the composition function, which I tend to do quite often, and then plug that number in. All right, evaluating a composition function. So if I want to find f of g of negative 2 here, I'll do it my way of Okay, this is the same thing as f of g of negative 2. First thing I'll do is find f of g of x. So that means I'm looking at 1 over 4 over x minus 1 plus 2. So now, I'm not going to do the hard stuff yet. I'll save that for the next slide. Now that I have this is equal to what f of g of x is. Now that I have this, I'll actually go ahead and say, all right, I've got 1 over 4 over negative 2 minus 1 plus 2. So this is 1 over 4 over negative 3 plus 2, which is equal to 1 over 4 negative 4 over 3 plus 6 over 3, which is equal to 1 over 2 over 3, which is equal to 3 halves. So my answer here would be 3 halves. I can go ahead, once I've figured out my composition function, I can plug it all in, and that would be what my answer is. We'll do the same thing with g of f of 3. So this means that I can first find g of f of x, which would be equal to 4 over 1 over x plus 2 minus 1, because I've plugged my entire function f into the x for g of x. Now that I'm here, I can actually go ahead and plug in that 3. So I can say 4 over 1 over 3 plus 2 minus 1, 4 over 1 over 5 minus 1, 4 over 1 over 5 minus 5 over 5. This is 4 over negative 4 over 5. This is 4 over 1 divided by negative 4 over 5. This is 4 over 1 times 5 over 4. And this is all negative. Those cross out. And negative 5 would be my answer here. So that's how I figure out my composition function. A lot of arithmetic there, but it's arithmetic we should know. So I can figure out my composition function that way. Now, I did kind of cheat here, and I'm going to cheat because I'm going to show you here. Using the previous functions, find g of f of x and state the domain. So g of f of x we've already found up here. So I'm going to go ahead and copy this and paste it down here. This is what g of f of x looks like, but I can't leave it like this. This is an improper fraction. We are not cool with improper fractions. What I need to do or this is a complex fraction, not improper, sorry. This is a complex fraction. We are not cool with complex fractions. So what I need to do is get a common denominator for my denominator. So I'm actually going to go through, and I'm going to multiply this by x plus 2 over x plus 2. So now I've got 4 over 1 over x plus 2 minus x plus 2 over x plus 2. So this is 4 over 1 minus x minus 2 over x plus 2, which is equal to 4 over negative x minus 1 over x plus 2. Now I'm going to go through and I'm going to simplify this. This is the same thing as saying 4 over 1 divided by negative x minus 1 over x plus 2. We're dividing by a fraction, so we flip the second and multiply over negative x plus 1, or x minus 1, sorry. And then I'm going to distribute that 4, so I end up with 4x plus 8 over negative x minus 1. So this is actually what the composition function g of f of x, which is the same thing as g of f of x, looks like. So this is that composition function. This would be my answer for what the composition function is. I had to go through, I defined that common denominator, I had to use that common denominator, and then simplify using fraction division. It's complicated in the sense that there's a lot of steps, but this is nothing that we're incapable of. We've been working with common denominators a lot. We've been working with these fractions a lot. We've been dividing by fractions a lot. Yes, there's a few more steps. Yes, we have to pay attention to those details. I would love trust me, I would love just as much as you if I could say that this here was my answer. But unfortunately, we can't. We have to go through, and we have to present this as a normal fraction. I can't have a complex fraction. I can't have a fraction within a fraction. If I have a fraction within a fraction, we have skills to do that. That's division. That's fraction division. We'll work with it. It's not okay. We have to go through and we have to fix those. So it is something that is a little bit of an annoyance. I get that, but you work with your common denominator, you figure out what you need, and you go from there. All right, now figuring out the domain of this function is a little bit more complicated. As a reminder, f of x was equal to 1 over x plus 2. G of x is equal to 4 over x minus 1. Here your domain is x can't be equal to negative 2. Here your domain is x can't be equal to positive 1. So when I do a composition function, when I make my domain of this overall composition function, so when I'm talking about this domain here, I start out with all values of x, like always, where x, first thing, x cannot be negative 2 in this case, and it can't be negative 2 because f of x is my inside function. And since f of x is my inside function, I can't plug negative 2 into f of x. If I plug negative 2 into this function, it just doesn't work. Because I'm saying, all right, I already have f of x. If I plug negative 2 in, I get undefined. I can't plug undefined into g of x and get some answer. It's not like that's a value that works. I can't say, if I plug undefined into my function of g, what is that number? That is not math. That's not how that works. That's unfortunate for us. So right away, I say that f of x can't be that domain. The next thing that I do is I'm going to look at my equal to negative 1. So g of x cannot be equal to positive 1. G of x can't be equal to positive 1. But I don't plug positive 1 in my function. If I plug positive 1 in my function, the first place I plug it in is f of x. So if I plug x is equal to 1 into f of x, I end up with 1 over 1 plus 2, which is 1 over 3, which means I can plug 1 into this function. If I plug 1 in, I get a value that I plug into g of x, which I can work with. What I can't do is plug something into my function f of x that gives me 1. F of x cannot be equal to 1, because if I plug something into my f of x that gives me 1, then I find g of 1, and g of 1 is undefined. So what I do is I figure out, okay, I'm going to set f of x. I'm going to say 1 over x plus 2 is equal to 1. And I say, all right, now I'm going to figure out, because this is my g of x, what x can't equal. And this is f of x, which is my input for g of x in g of f of x. I find that 1 is equal to x plus 2 when I multiply both sides. I subtract 2 on both sides, and I end up with x cannot be negative 1. And you would find there that, okay, yes, when I actually did my original math, that worked out. I could look at that final denominator. That final denominator is a good hint as well, but this is the technical thing that I should be doing from the get-go. I should be saying, what is my output of f of x? What number would I plug into f of x that gives me an output that I can't plug into g of x? I can't plug positive 1 into g of x. I get that positive 1 from f of x, from the function. So what x value do I plug into f of x that makes it equal to positive 1? And when I look here, 1 over negative 1 plus 2, that's 1 over 1. That gives me an f value of 1. That's not okay. I can't plug this in. So my domain here is all values of x, where x cannot be equal to 2 and x can't be equal to negative 1. And I had to figure out, okay, what is my value of x that I plug into f of x that's not going to work for g of x? And that's a little bit complicated, and we'll touch on this a little bit more in class because I really want to drive this home. But that is how we figure out these domains. It's a little bit more complicated. All right, equal composition functions. So I'm telling you right now, these are equal composition functions. How do we figure out that they're equal? So I'm going to figure out what f of g of x is, which is the same thing as this. F of g of x is 3 times 1 over 3 times x plus 4 minus 4. These cross out. I'm left with x plus 4 minus 4. These cross out. f of g of x is equal to x. G of f of x, this is the same thing as g of f of x, where I'm plugging in my entire function f of x into my g of x function. So I've got 1 over 3 times 3x minus 4 plus 4. I work in parentheses first, so this is 1 over 3. These will cross out, times 3x. These will cross out, and g of f of x is equal to x. So, if g of f of x is equal to f of g of x, and both of these are equal to x, then we say that we have equal composition functions. And they should always be equal to x. If your composition functions are equal, that means your composition functions are equal to x always. So both composition functions equal x, therefore they are equal composition functions. And then breaking down composite functions by parts, this is something that some students struggle to see, and that's okay. It is a little bit of abstract thinking, but this is something that is huge. You're going to be breaking down composition by functions by part all the time in calculus. This becomes a really, really large part of, can you differentiate by parts? Can you integrate by parts? Can you break down your function? Can you look at it in different ways to make your life a little bit easier? So suppose that f of g of x is equal to h of x, and that h of x is equal to x squared plus 50. What would be the composite parts of the function? So here, the easiest thing to look at is say that I've got x squared plus 1. It looks like I've got a function x of 50 with another function x squared plus 1 that has been plugged into that function x to the 50th power. My inside function here is g of x. My function that I'm plugging it into is f of x. So when I look at this, I'm going to say g of x is equal to x squared plus 1, and I'm going to say that f of x is equal to x to the 50th power. And then if I make f of g of x, this is something that's really easy for me to check. I plug it in, f of g of x is equal to x squared plus 1 to the 50th power. And when you look at that, that's how it works out. So when I'm breaking down my composite function by parts, I'm just trying to basically say, what makes sense to be input into something else here? What is the idea that makes sense of inputting into another thing? I could make another composite part of this function, which is, bear with me here, I could say that f of x is in fact x squared plus 1 to the 50th power, and I could say that g of x is equal to x. And when I plug that in, that works out. I don't really like that. That's kind of cheating. I could always just say my g of x is equal to x or whatever. So when I'm breaking down this composite part, technically these are both composite functions. It's just that one composite function is way easier than the other. But this technically here is the more correct answer. If you're not breaking it down into something beyond x, you're not really doing yourself any good for the future. So here I'm saying that g of x is x plus 1 and f of x is x to the 50th power. Got a homework assignment tonight. If you have any questions or concerns, please reach out as soon as possible, and have a great night.